Hi boys and girls, this is lecture 5.2, Antiderivatives and Indefinite Integration, part 2 of our discussion. In the previous lecture, we saw how integration yields a family of antiderivatives. But it is possible to find a particular solution out of the infinite solutions we find if given an initial condition. An initial condition is usually just a point on the curve. For example, this diagram shows several antiderivatives of the form the integrand 2x plus 2 dx, which integrates to x squared plus 2x plus c. We see x squared plus 2x plus 4, x squared plus 2x, and x squared plus 2x minus 3. And of course, there are an infinite number of solutions in this family. Given a specific initial condition, such as f of 0 equals 4, a particular solution can be determined. So if our general solution is f of x is equal to x squared plus 2x plus c, let's use the fact that we're talking about the curve that has this ordered pair on it. The curve that has the ordered pair 0, 4 is the one we're looking for. And plug that in for x and the function value y in order to solve for our specific c. That means 4 will have to equal 0 squared plus 2 times 0 plus c, which means c has to be equal to 4. Therefore, out of the infinite number of solutions that we have, using this initial condition, we narrowed it down to the specific one that we are interested in, which is x squared plus 2x plus 4. That is the solution that has the ordered pair 0, 4 on it. Find the general solution of f prime of x equals 1 over x squared, and then find the particular solution that satisfies the initial condition f of 1 equals 0. That just means we're going to look for the curve that contains the ordered pair 1, 0. But first, let's find the general solution of this differential equation. We're going to integrate 1 over x squared dx. I can rewrite that as x to the negative 2 dx. Now integrating using the power rule, if I add 1 to negative 2, I get negative 1, and dividing by that new exponent gives me negative x to the negative 1 plus c, which can be rewritten as negative 1 over x plus c. So the general solution to that differential equation, f of x equals negative 1 over x plus c. Now notice that several of these curves have been graphed here with a variety of c's, but we're now going to hone in on one particular curve, the one that goes to the point 1, 0. That initial condition will allow us to now select a particular curve from the infinite number of curves in that general solution. So the point 1, 0 means that the x value is 1, the function value or y value is 0. Let's use that in this general solution to specifically determine a c. 0 is equal to negative 1 over 1 plus c, which means 0 equals negative 1 plus c. Therefore, c has to be 1. That means the specific solution that we're looking for then will be negative 1 over x plus 1. We can use initial conditions to solve vertical motion problems. First, let's remember the relationship between position, velocity, and acceleration. If we let s represent position, then s prime is v, velocity, and s double prime is v prime, which is a, acceleration. Now, since we are taking antiderivatives, we're going to work backwards from acceleration to construct a velocity function, and backwards from velocity to construct a position function. But we'll need initial conditions to do this. So let's see what initial conditions we have in this problem. A ball is thrown upward with an initial velocity of 64 feet per second. That means at time 0, velocity was 64 feet per second. And since it was thrown upward, our velocity is positive. Then from an initial height of 80 feet, which means at time 0, position was 80 feet. With these two initial conditions, we'll be able to work backwards from acceleration to a particular position function, which is what is asked for in letter A. Find the position function given the height s, giving the height s as a function of the time t. We'll start with the acceleration due to gravity, which is negative 32 feet per second squared. So for letter A, we'll start with the fact that velocity is the integral of acceleration. Therefore, we're going to integrate negative 32 with respect to time. This gives us negative 32t plus c, our general solution. But using the initial condition that we have, we can solve for a particular c. 64 is equal to negative 32 times 0 plus c, which means that 64 equals c. Therefore, our particular velocity function is going to be negative 32t plus 64. Position is the integral of velocity. So our position function will be the integral of negative 32t plus 64, of course integrated with respect to time. The integral of negative 32t to the 1 is going to be negative 16t squared. The integral of 64 will be 64t, and then plus c. Once again, our general solution, negative 16t squared plus 64t plus c. But using the initial condition, the fact that at time 0 position was 80, we will solve for a particular c. So 80 is equal to negative 16 times 0 squared plus 64 times 0, which means that 80 is equal to c, and therefore our particular position function will be negative 16t squared plus 64t plus 80, and that is the answer to letter A. Now for letter B, we are asked when the ball hits the ground. When does the ball hit the ground? And the way we're going to find that is take our position function and set it equal to 0, because when position is 0 is when the ball is on the ground. So 0 equals negative 16t squared plus 64t plus 80. Let's factor out the negative 16. That gives t squared minus 4t minus 5. Dividing both sides by negative 16 gives 0 equals negative t squared minus 4t minus 5, which factors into t minus 5, t plus 1, giving two potential answers, 5 and negative 1. We can rule out negative 1 since we know that time cannot be negative, which means at 5 seconds the ball hit the ground, and that is the answer to letter B. As previously mentioned, one of the most important steps in integration is rewriting the integrand in a form that fits the basic integration rules. So let's get some practice doing that with these examples. Here is the original integral, 2 over the square root of x. This can be rewritten as 2x to the negative 1/2 dx. To integrate, we'll add 1 to negative 1/2. That gives us a positive 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal 2. Since there's already a coefficient 2, that's going to give us now a 4x to the 1/2 power plus c. That can be rewritten as 4 square root of x plus c. In letter B, we're going to have to multiply these two binomial factors together in order to integrate. This gives us the integral of t to the 4th plus 2t squared plus 1 dt, which means the integral will be 1/5 t to the 5th. Remember, we're just adding 1 to the exponent and dividing by the new exponent. And then we'll have 2/3 t cubed plus t plus c. In letter C, we'll first of all rewrite this by dividing each term in the numerator by the monomial x squared. So this can be rewritten as x to the 1 plus 3x to the negative 2. Now using the power rule, we're going to have 1/2 x squared, and then adding 1 to negative 2 is -1. Dividing by that gives us now a -3 x to the negative 1 plus c. This can be rewritten as 1 over 1/2 x squared, and then -3 over x plus c. And finally, let's rewrite this integrand by taking x to the 1/3 and distributing it to both terms in parentheses. This will give us the integral of x to the 4/3, because 1/3 plus 1 is 4/3, minus 4x to the 1/3. Integrated with respect to x. Now adding 1 to 4/3 is 7/3. Dividing by 7/3 is equivalent to multiplying by the reciprocal 3/7. So this becomes 3/7 x to the 7/3. Adding 1 to 1/3 gives us 4/3. Of course, dividing by 4/3 is equivalent to multiplying by the reciprocal 3/4. -4 times 3/4 is -3x to the 4/3 plus c, and that is the simplified form. That's it for today's lecture. I hope this true statement makes you as happy as it makes me. God bless you, boys and girls.